we have Eileen Li, who will be talking about linkage errors in the IDI. So Eileen embarked on her journey with the IDI in 2018. She is a member of Compass Research Centre at the University of Auckland, where she has actively contributed to various projects focusing on child poverty and health outcomes, as well as the impact of delivery mode on educational achievement. In her most recent endeavour, her PhD project investigates linkage errors in the IDI and explores potential strategies to mitigate linkage bias. So, thanks, Eileen.
Thank you, Natalia. Tēnā koutou katoa no hana aho. Kei tamaki makolo toku kainai nei ko Eileen Li toku ingoa. Nonela tēnā koutou katoa. Hello, everyone. I'm going to talk you through my project looking at linkage bias and linkage errors in the IDI. You probably know that record pairs in the IDI are linked through probabilistic linkage, and that means a matching weight is calculated for each record pair, and a threshold is chosen such that records with weight above this threshold are considered true links. This probabilistic linkage process will inevitably introduce linkage errors to the linked datasets, and they can be false links in the top right corner or mislinks in the bottom left corner. So an example of a false link would be my census record get linked to Natalia's text record. And a mislink would be, say, I filled out census form, but somehow my census information didn't get linked to the IDI central span. That's a missed link. There's always a trade-off between these two types of errors. If you are familiar with statistical terms, these are the type 1 and type 2 trade-off. But otherwise, just think that the total amount of linkage errors remain the same, but the composition may change depending on what threshold you choose. If you increase the number of false links, you will have fewer mislinks. But otherwise, if you have fewer false links, you would have more mislinks. So there's always this trade-off between these two types of linkage errors. What I'm about to show you are not official statistics because I used the IDI, and this is a disclaimer that the data are not official statistics. They are only my research findings. Let's begin with the identification of false links. We know that the IDI is made up of a central table called the spine and multiple node datasets. Records are linked to this central table spine first before they can be linked to one another. We also know that the IDI gets updated or refreshed every 3 to 4 months to reflect data changes or the addition of new datasets. So I come up with, based on this special feature of the IDI, I come up with this inconsistent spine approach to identify probable false links. Basically, this approach looks at the linkage pattern between the node dataset and the spine over time and pick up the ones that did not get linked consistently. So if we look at the pattern on the next slides, there are 3 possible patterns that we can get. Example 1 and example 3 are not the ones we are interested. We are interested in the second one. So if this link get linked to the spine at certain refreshes but not the others, these are the iffy links and these are my probable false links. So as illustrated in example 2 here. Using this approach, I've identified about 12,000 probable false links. And the reason I call them probable is because there is no way to validate these are the true linkage errors because the person's identifying information such as their full name, their full date of birth are not available to researchers using the IDI. Using this approach, I've identified about 12,000 false links. And here is the distribution by ethnicity. One thing to note is that the missing ethnicity category actually contributed the most to the overall number of false links. Identifying false links for one node to spine linkage is the first step. The next step is to assess how much bias will false link cause on linked data analysis. And speaking of linked data analysis, there has to be more than one node dataset. So in my case, I've chosen census data and education data as my two node datasets. So here I'm trying to link census records to the spine and from spine to education datasets. So essentially, I'm linking from census to education. What I did next is this replacement approach. So to replace the replacement approach is basically to replace the false links outcome with another records. In this example on this slide here, the first three columns are from census. So sex, ethnicity, and income are from census. And I'm interested in looking at the relationship between income and educational achievement. So this percentile column in blue comes from the education datasets. So you can see that my data, more than half of it comes from census. The information comes from census, and the rest come from education. What I did with this replacement approach is to replace this potential false links outcome with another record. And this another record is what this false link is likely to be confused with. By doing this approach, I can tell how badly my estimated coefficient will be affected if the false links all had wrong values on their outcome variable. So in this case, the third record, this male Asian, is likely to be a false link, and this person has a percentile score of 0.11. And because this one is likely to be a false one, I'm going to throw away the 0.11 and replace, say, 0.41 from my pool of candidates to replace that value, which you can see from the next slide. This is my dataset after this replacement. So I've done, because at each time I randomly select a outcome from this pool of candidates. I've done this process 200 times to reflect all the variation that can happen. After every replacement, I run my linear regression one time to obtain the beta 1 coefficient, which you can see from the next slide. Yes, so this is the model I've run. And because I've done this replacement 200 times, I've also obtained 200 beta 1 coefficients. And I've plotted my beta 1, 200 beta 1 coefficients on the next slide. So this green curve indicates the 200 beta 1, and this blue vertical line represents the naive beta 1 estimate, assuming the data is linked perfectly. What this plot tells me is that there's no overlap between my naive estimate and my 200 times the distribution of the replaced results. This bell curve also indicates is 95% empirical confidence interval. So there's no overlap, indicates that the bias is statistically significant. However, I'm showing you a statistically significant result on a tiny scale that goes from 1.9% to 2%. And that's for an outcome that ranges from 0% to 100%, which is the percentile score. So if I zoom out to the full scale, which you can see from the next slide, you can see that the difference, the differences between the replace the results and the naive estimates is essentially there's no practical significance at all. So that's for the false links. We've also looked at mislinks, which unfortunately I don't have the time to talk today.
What I've noticed when I've been doing some not similar, just on an informal basis, is quite often you can pick up false links through dates of birth. Have you kind of looked at consistency of dates of birth across different data sets?
Well, yes, date of birth is definitely one possibility. We've looked into this impossible scenario approach where we looked at different, so if people have different disagreeing information on those key variables, or people that's definitely not going to be the same person. For example, this person died in 2010, and then this person filled out census in 2013.
Yeah, I've had someone.
It's not going to be the same person. It's definitely two different person.
Yeah.
However, they got linked together. We've looked into those cases, but I have to say that using those impossible scenario to identify false things only gives you a minimum size of false things. And we are interested in coming up with an approach that can look at everyone in the population and come up with a score, an indicator that's at individual level. So it's not only look at those impossible scenarios, but it gives a broader coverage of false link identification.
Yeah, and because I find that I don't notice this, and then all of a sudden I realize there's something funny going on, like there's someone with 127. What should we be doing, like when we're using the IDI in general for our analyses to like mitigate for this, or do we not need to because it's all probabilistic matching, so it's okay?
I guess it really depends on how many node datasets you are using. In this case here, I've only used the two, which is probably oversimplified situation, because most of the time you'd need at least three or more. So one is that you need to, it depends on how many node datasets, and also depends on obviously the more node datasets you have, the more false links you are likely to get. And secondly, I think my opinion is that false links are linked to people that share similar characteristics. So even if it's a false link, it's likely to link to a person that has similar outcomes. So false link may not be the biggest issue. Also, knowing that Stats New Zealand has quite a stringent threshold on capping false link rate. So for every single node to spine linkage, the false positive rate is capped at 2%.
Yeah.
So yes. So yeah. To sum up is that false links are small.
But bigger for some groups, like they're higher for Pacific peoples, we know.
Yes.
Where it worries me when you start looking at smaller groups who have higher false linkage.
Yes.
Yeah. Anyway, I'll stop.
So the denominator is those people who were inadequately matched, or everybody who was matched and those who aren't matched. Are you trying to achieve matching in those people who were matched by no other sources, or are you including people who are adequately matched? Because you've shown that the ethnicity of the largest group of unmatched ones, the missing ones, so they're going to be missing a whole lot of other things. Are they just floating in the milieu, waiting to be matched to something, and they're excluded from all the other matching?
Yes. So the denominator is people who got linked, and the people who didn't get linked are the missed links. So it's a whole different problem to these false link problem. And I think you mentioned that people who are missing ethnicity, you mentioned something missing. Yes, so there's people who got linked, but still show this missing ethnicity, and that's because maybe the data is not complete for those records, but somehow because they have other information, they still got linked, and because they got linked, I can identify them as false links. If they didn't get linked at all, those would be the missed links.
There is a question in the chat now.
Thank you.
It says, your mentioned method, is it similar to multiple imputation of missing data?
It's not similar to multiple imputation of missing data. I'm not going to impute the data. I think the goal of multiple imputation is to make sure your data set it doesn't have missing value, or are you trying to fill out values so that your analysis will be okay to run without dropping out too many observations. But my goal is to see how much bias could those false links cause on my linked data analysis if those, and potentially particularly if those false links all had wrong values on the outcome value. So this provides the upper bound of the bias for the analysis that I'm looking at. So to answer your question in short, no, this is not similar to multiple imputation.
But some of what the IDI does in terms of the matching, they do some imputation on some variables, at least from sensor.
That's a very interesting topic. I can just keep talking. They don't do multiple imputation. They do this very old schooled hot desk imputation. So they pick a record that's similar to this record that has missing values and just pick the fill out the value from this similar person.
Thank you very much, Eileen.